Everyday mathematics.
So today we are back at it again. This is another interesting problem that involves floor function, but today we're adding another layer of this discretization of continuous functions, which is a ceiling function. This problem comes from the MIT 2023 Integration B regular season, problem 14. And as you can see, it's the integral of floor function of x times the ceiling function of x from 0 to 100. So how you would begin attacking this problem, first of all, even before I jump into that, I would like to rehash and redescribe what a floor function is. This is a function that takes a real number x and gives an output that is a whole number integer less than that real number. For example, if you take in 1.5 and feed it to the floor function, it would give you 1 as the integer lower than that. 1.4 still you'd get 1. If you fed in 1.8, you'd still get 1. And then if you fed in negative 1.5, then the integer less than that whole number integer would be negative 2. And then if you also fed in negative 2.5, the whole integer less than that would be negative 3. So we have this graph that is shown here. First, let's look at the interval from negative 2 to negative 2. The flow in that region is going to be negative 3. Then from negative 2 to negative 1, the integer lower than that within that interval, excluding the negative 1 point, is negative 2. Then between negative 1 and 0, within that region, the flow is going to be negative 1. And between 0 and 1, the flow is 0. Between 1 and 2, the flow is 1. Between 2 and 3, the flow is 2. Between 3 and 4, the flow is the integer lower than that, which is 3. And then between 4 and 5, the lesser integer there is going to be 4. Now, what again is a ceiling function? A ceiling function, on the other hand, is the integer, whole number integer greater than the specific real number that we're looking at. For example, if you had the ceiling function of 1.5 would be 2, which is the integer, whole number integer higher than that. 1.4 would be 2, 1.8 would be 2, negative 1.5. Now, instead of negative 2 with the floor function, the ceiling function will give you negative 1. And the negative 2.5 input would result into a negative 2 output with the ceiling function. So that if you have a graph shown there for y is equals to the ceiling function of x between negative 3 and negative 2, instead now you'd have negative 2 as your output. Between negative 2 and negative 1, the ceiling there would be negative 1. Between negative 1 and 0, the ceiling there would be 0. Between 1 and between 0 and 1, the ceiling is 1. Between 1 and 2, the ceiling there is 2. Between 2 and 3, the ceiling there is 3. And between 3 and 4, the ceiling is 4. That's the much about it. Now, so for our problem, if we have the value of x between two integers k and k plus 1, for the floor function of x, it will be x. That will be the output of that function. Now, if we look at the ceiling function between the same two integers, the value of the ceiling function would be k plus 1. So now looking at our integral, the product of floor function x and ceiling function of x, would result now into a summation of these very many strips that you have. So you have these intervals between integers, whole number integers, but within those integers now we have two functions. We have to deal with the floor function, which is k, if we're looking at between k and k plus 1, and then the ceiling function, which will be k plus 1, and then x is x in between there. So we have the product of the three numbers, two of which are whole numbers. And then we can sum the strips up, but within those strips we'd have to integrate the value for x to get the area beneath the curve. So that now results into us pulling us the product of k and k plus 1 out, and now we would integrate for x between k and k plus 1. And that now means that we have k squared plus k, and then we have x squared over 2 integral from k to k plus 1, right? Then the next step now results into substituting these intervals, these limits, into the x squared over 2, and we have k plus 1 squared minus k squared. And then we can now use the product of the difference and the sum of these two numbers, and that would mean that now the eventual sum would be k squared plus k times k squared minus k, which is k plus 1 minus k times k plus 1 plus k. So the k and the k here cancel, and we remain only with 1. So it eventually becomes a summation of half, summation from k from 0 to 99 of k squared plus k times 2k plus 1. So when we multiply the two things together, we get a summation of 2k squared plus 3. This is actually 2k cube, so I should be very careful here. Cubed plus 3k squared plus k. Now, one interesting notation that we have, this is something that is in a lot of books. When you sum the k squared value, let's begin with k. When you sum k from 0 to n, that summation results into n times n plus 1 over 2. Now when you do the same for k squared. This is a well-known formula. It's n plus 1 times 2n plus 1 over 6. And then for k cubed, you get n squared plus n plus 1 squared over 4. Now the derivation for this summation has been done by the gentleman Black Pen, Red Pen. The link for that derivation is included in the description. I really encourage you to go and look at how neatly he was able to actually derive or show that the summation of k squared, and k cubed result into what we're showing here. But all the same, these formulas are included in many of the textbooks and can easily be gotten online as well. So what we're going to do now is we're going to plug where we have k here, the sum of all the k integers from 0 to 99, where n shows up, we put in 99. And the same thing for k squared and k cubed. So as you can see here, we have a half outside, and then 2 for k cubed term, we have 99 in place of n, 99 squared, times 99 plus 1, which is 100 squared over 4, plus 3 for the k squared. We have for n is 99, n plus 1 is 99 plus 1 is 100, and then for 2n plus 1 is 2 times 99 plus 1, which is 199 over 6, plus n times n plus 1, which is 99 times 99 plus 1, which is 100 over 2. So when you add up these values together, you eventually get 24,997,500. So this is our final answer. Very interesting problem, but the answer is straightforward. Thank you very much. For those of you who have not subscribed to our channel, again, I do encourage you to subscribe. We're going to be really handling a number of problems pertaining to floor, ceiling functions this week. And I hope you join us in this journey to really bring light to some of these intricate and complicated functions. Thank you very much, and I hope to see you tomorrow again.